Good afternoon, everyone. It's 3:30, so we'll go ahead and get started. Welcome to today's hybrid EOL seminar. I am Sarah Woods, and on behalf of EOL, I'm pleased to introduce Professor Alexander Kostinski, an EOL affiliate scientist. Professor Kostinski holds a bachelor's in mathematics from Hebrew University in Jerusalem and a PhD in physics from the University of Illinois. After a postdoc in electrical engineering at Illinois, he joined Michigan Technological University, where he has taught and conducted research since 1989. Professor Kostinski's extensive background includes designing and teaching a new course on environmental thermodynamics and serving several years as editor for Reports on Progress in Physics. His impressive and extensive research spans from the foundations of radar polarimetry to droplet clustering in turbulent clouds, imaging of extrasolar planets, and precipitation physics, amongst other realms of physics. Please join me in welcoming Professor Kostinski for his intriguingly titled seminar, Glints, Glories, and Signals. As a reminder, if you're watching online, please feel free to enter your questions in Slido at the bottom of the screen, and we'll take those during Q&A. Professor Kostinski has asked that anyone in the audience, if you have a pressing question in the middle of the talk, please do feel free to raise your hand and I'll come at you with the mic.
Hi. Thank you, Sarah. And yes, I prefer actually to interrupt at any time. And it'd be nice not to wait. And it's not very long talk. And I want to thank Vivek for inviting me. It's a nice opportunity. So I'm here as an affiliate scientist. So this is a little unusual, this talk. I just put it together to convey the sense of what I've been doing recently. But this topic that I just put here last night, in fact, after talking to Vivek, is just to indicate my purpose is not to show off, but to simply indicate what might be possible topics for a conversation. So, yeah, and so I'm here and hope to be of some use to EOL, and my purpose is mutual understanding, not the speed of transmission. So please go ahead and interrupt whenever it's not clear. So I'll just try 3 different topics because it happens that I've done it last few years, and it may be of interest to you, I thought. And this is simply a list of papers on part 1 on Glints. And I will not, most of it I'll leave alone, but the interesting part I think about this work is that it's very far away, and it was a big surprise. And some microphysics here might interest you. So I'll talk perhaps about the very first and the very last article. And so let me try to explain it. So this is the setting. The Discover satellite is about 1 million miles away. And so my friend there at Goddard Space Flight Center, he's actually a mathematician by education, ended up being in charge of this camera on board of this satellite, sorry. So this satellite is a so-called Lagrangian point, right? So it's sitting there and it's looking at the sunlit face of the Earth constantly, all the time. And it's available at night easily. It's very, very pretty. And so the whole thing started literally with a 3-minute conversation. And Sasha, it's Alexander Mashak, Sasha is his Russian nickname, like mine, by the way. And he asked me about this bright flashes that we saw. So I'll tell you about this unexpected bright flashes. In retrospect, it seems almost trivial, but at the time, it looked like a mystery. So we are looking at the sunlit face of the Earth, and so this little, I can use the cursor right here. This little square is a zoom in on the actual flash. It looks a bright flash. It looks colorful because I'll explain it in a minute in more detail. Because the camera takes pictures in 3 colors at slightly different times. I'll show you a picture in a minute. But just to give you the feel for the numbers, the 10 kilometer is a pixel size. Angular spread is very small. And so EPIC is the name of this camera. So that's how we started. What is the physical origin of this spot? And I think before this, Voyager, I think, saw these spots. And actually, there was a paper by the famous astronomer, Carl Sagan, about these glints of the ocean surface. And they wrote a paper in Nature, and in fact, used it to practice on Earth as an quote, exosolar planet to see if what could be recovered. But as far as I know, no land glints have ever been seen. So when we saw it over land, it was a puzzle. Well, ocean we know can produce glints, but what can produce glints all the way to that far, million miles away over land? Turned out ice crystals, and it seems simple in retrospect, but I'll tell you in a minute. So this is a little bit about the camera that sits on this Discover spacecraft. So it has the 3 filters, right? The color filter. It has other channels as well, and the timing is such that the blue filter, and I think the blue image has the highest resolution, precedes the red one by about 4 minutes. And the green is somewhere in between. And so when there is a scatterer in the field of view that scatters very strongly, then you'll see the different colors as well. And so that's an interesting number is that the glint shifts here during this 4 minutes, 100 kilometers. So it's really the curvature of the Earth during this period that normal to the Earth's surface that matters. Okay, so these were the typical glints, for short, that we found, the bright flashes, and you can see them now almost on a daily basis. It's available in fact, NASA made them a product, but at the time it was very very strange, and so we found a whole bunch of them. I'll give some numbers here. Now we have more data, but the right image, I think, was the first one we found, and we called them birds because of these wings. And the wings are there because not only are these things bright, send enough light million miles away, right? Not are they bright, but they're super bright in the sense that they saturate the CCD detector. And so these wings are actually a spillover. Neighboring pixels in the detector get extra electrons, photo-induced electrons. And so that seemed amazing to us that they can be so strong. And a couple of possibilities that were suggested, actually even the reviewers didn't believe it for a while. So cosmic rays was one possibility. Thunderstorms, lightning, and it was another possibility. It turned out that it's ice crystals. And so that was the conjecture. And how do you prove it? So we proved it with geometry. And there was fortunately lots of observation available that you'll see in a minute. But what's puzzling is that, again, the intensity of this reflection, nearly horizontal orientation for ice crystals. So let's remember this notation that for a minute, that solar Earth vehicle. So this is just the angles involved, okay? The angles involved. So the conjecture is that it's ice crystals. And then, of course, once we managed to confirm it, then one could study ice and clouds. It's sort of amazing that one could study statistics of cloud cover, mixed phase from 1,000,000 miles away. It sounds very strange at first. But just to get you in the mood for glints, yeah, I wanted to mention to you. Actually, the picture on the right I'll need it later to share with you some puzzles. At least I didn't understand it at all. The current stage of this research. But the glints on the right, of course, we've all experienced it, but the width of this sort of glitter depends on the distribution of slopes, little facets, water facets that scatter light, right? The rougher the sea, that's how they monitor winds sometimes, right, from spaceborne devices. The rougher the sea, the broader is this set of glints, right? And but as we'll see later, they're actually much narrower from crystals. And on the left is this is mostly for fun, but it's actually of some relevance, as we'll see later. It's a famous painting by Vermeer, and I think it's entitled "A Girl with a Purple." I'm sorry, a girl with
Pearl earring.
pearl earring. I think that's it. Thank you. Yeah, pearl earring. And so I came across it because some astrophysicists just a few years ago. I was looking for glints elsewhere. It's a totally unexpected Google search, and he discovered that this glint off the pearl earring is off, and he claimed that it's not pearls, and somebody else touched up this painting and so on. But if you look closely, painters use glints to great benefit because even in the eye, eyeballs, and specular reflection, optics, very interesting. Up until about 4 or 5 years ago, I never really thought of it much, specular reflection, but those ice crystals got me into it. So before I show you what we consider a pretty reasonable proof, I wanted to get some numbers. It's a boring slide, but nevertheless, I want to share it with you just to prepare for the next slide. And so the Earth tilts, and this gives a range of what of a possible range of latitudes at which we could see glints. And then there is a specular condition in the second paragraph, right? And so it wasn't all that trivial because there's three-dimensional geometry involved, and so that couplanarity in particular. But so we began to compare. See if we can go plus minus 25 degrees, let's see where we observe the glints. So it took about a year or two for the picture to emerge. And this is on the left is the location of flashes for that 1 year of data. And you can see they're color-coded in accordance to how they were detected, with which channel, right? And it really coincided with the range of the satellite. So, and then we plotted it on the right, latitude versus time of year, and that was pretty good. You could see the fit. There's pretty little scatter, so they all fall on where they should. So what that proves is that this is definitely specular reflection. So I think that it also proves that these are ice crystals, horizontally rated ice crystals. What else could do it? But we should probably keep an open mind just for surprises. But our current understanding is it's ice crystals. Ice crystals, plates which are horizontally oriented. And that's simply because we cannot think of anything else to do it with that kind of intensity. And these super glint saturated detections. And then once you decide that these are ice crystals, then you can turn the question around. Oh, let's monitor the population of crystals, likelihood of their occurrence, and so on. What's the likelihood of clouds with mixed phase? And surprisingly, so we wrote a couple of those papers are actually on statistics, statistics of monitoring ice clouds. So and it agreed very well with other methods. Here's the fraction of occurrence of ice in clouds for such and such latitude and so on. So that worked pretty well. And then we got interested in super glints. It was one paper, and mostly because it was just so perplexing how they can manage to send enough energy a million miles away. And I tried many back-of-the-envelope calculations, and in that paper we also reported on a small lake. The lake is literally, so the pixel size is 10 by 10 kilometers, but the lake in the Andes was about maybe 1 by 1 kilometer. Relatively small fraction of the pixel, maybe larger, but less than half a pixel, and it still saturated the detector. And so, and the question is, well, it's even of some interest to astronomers possibly. If you can see this that far away, maybe you can see the next exosolar planets.
What is that theta not in the previous one? What is that angle 4 degrees here? Next slide.
Next slide.
What is that angle refers to what?
This angle was discovered epic. Let's theta naught. It was I think I think it was a tilt angle of the possible specular reflector. You know, I'm not so sure anymore, but I think.
So I was wondering, this kind of correlates with HSRL, that 4 degrees of tilt and HSRL.
Yeah. So I'll address it. Yeah. So to be honest, I don't remember how what was taken here at 1139, but we are thinking it was the case of ice crystals, but I'll address this angle and define it very precisely in a 3 or 4 slides. You're talking about 0 versus 4 degrees for the glint of ice crystals. Yeah. So yeah, so our observations are in agreement with that, even narrower, which puzzles me. So I'll come back to it in a minute. Thank you. And on this one, to be honest, I managed to forget already. What's the theta naught? I wanted to summarize it first paper and don't remember. But I'll address the glint near angular spread. Just to give you an idea, this is still open, by the way, and it's maybe I put a sentence or two in one paper, but it's still open. Just how far is it? It occurred to me that it's very unusual for remote sensing in the sense that it's just an idea that there are 4 length scales, 2 longitudinal length scales and 2 transverse length scales. And you can ask the question, is it possible that these scatterers within a pixel could interfere constructively to give you a coherent return? And that's all to answer that question. How come it's such little things, micron, 10 to 100 micron big crystals can scatter that much light to a million miles away? And so maybe coherence could possibly play a role. So we shouldn't automatically assume maybe just radiative transfer, which by definition is incoherent. So that's a kind of a back-of-the-envelope calculation, but I thought I'd point it out. So that's a condition. And it turns out that the 2 transverse length scales should be the product should be much less than the product of longitudinal length scales. And it turns out that we are at the borderline, so partial coherence is possible in this scenario. Partial coherence is possible. So it's in that sense, it's quite possibly beyond radiative transfer. And just a thought. And then another unexpected application was this. This was a different paper, just to give you a flavor. So the idea was to turn the problem around and ask the following question. If you know it is specular reflection, and you know at which point specular reflection should occur, then one could certainly overall average reflectance, so averaged over years of data, should be higher at the point of specular. There might not be a scatterers there always, right? But if it is, reflectance should be higher. So averaged overall, how much higher is it, the reflectance? And so we began to look, and the 2 slides on the right are just an example of raw data. That question actually took us to unprocessed data, to the raw possible data, so to speak, level 1A. And we looked at the actual intensity recorded by the detector. And it did seem to be peaked around the specular reflection, but a bit off. And then a nice surprise happened, total surprise. And it turns out while we were working on these glints, now, to put it in context, glints are a nuisance to most people, right? In the remote sensing, glints are a problem, right? People throw them away. Agree? Because they interfere with the retrievals and, do all kinds of unpleasant things. And so usually thrown away. So it wasn't a lot to compare with, For example, in Modis, people throw it away and so. But while we were working on these glints, unbeknownst to us, software people were working on improved geolocation. They'll pick some coast, I forgot the coast somewhere in maybe particularly sharp boundary between water and land, I'm not sure. And they try to make sure that their geolocation is perfect. And so they had done it twice during this work. And then when we looked, it's from left to right, version 1, version 2, version 3. So totally different method of improving geolocation. What we found is that specular reflectance became progressively more focused. You see? You just plot the averages of average reflectance, all you do, and it begins to peak better and better. And so suddenly the conclusion is, well, perhaps you can use this maximum of reflectance to pinpoint the location. Geolocation can benefit from this, which was also kind of a nice, unexpected result. Here is this same result for a couple of different plots, particularly on the right. And you can see that it peaks more and more sharper, becomes progressively sharper. And mean reflectance, in this case, it was 780 nanometers we plotted. But. So that was one message. Another interesting surprise. Well, yeah, you can improve geolocation with this reflectance plotting. And it happened for all channels, so it was the subject of another article. And all channels did that. We can explain roughly why it diminishes at some channel, larger absorption, but that was the idea. And but now I'm coming to the question of angle, Vivek, like you asked, and that's 0 versus 4 degrees. So I'll show you the data in a minute. So here the question is, why are these glints everywhere? So we're not the only ones that measured it from ice crystals. There's literature out there where people see it from airborne platforms as well as from the ground. And when they see it from the ground, they literally point lidars away, typically by 4 degrees, as you said, right? And you guys do it also by 4 degrees, right? Now, why 4 degrees? I'm assuming it's based on this empirical evidence that if it's less than 4 degrees, the glints can interfere. There's all kinds of retrievals, right? And so, but here we are looking at the sunlit face of the Earth, and we can ask the question, what is the angular spread of this specular reflections or glints? So delta here denotes, right here, delta denotes the angle. We call it the glint angle, which is on the x-axis here, delta, which is the angle between the specular direction, that one pixel, the only one in the whole field of view, which satisfies that condition, and nearby. And and we see repeatedly, every color, every lecture, we see repeatedly that it's narrow, 1/8 distance here. So this is not quite maybe the most revealing axis for action of pixels with glint. It's statistical. I'll show us reflectance in a minute. But you already get a hint that it's about a degree at most, right? Half. Another degree on the other side. So you get 2 degrees. And so it's in the ballpark of less than 4 degrees, right? And then we do it, so here it's defined a little bit better, and I want to make the move to the particles themselves. So here we are taking this idea seriously, that these are ice particles, and mean reflectance over the one at, say, delta 3 degrees. I mean, is given here. And looks like, I'll talk about diffraction in a minute, but looks like diffraction, if this were diffraction, you'd have color dependence, but it didn't happen. So I think we're ruling out diffraction. And so maybe you can focus on these 2 plots. So here, the glint angle, which is optics, it's observation. Optics tells you something about the orientation of the particles. If this is a source of specular scatter, right, then it's something strange happening. These particles apparently are so well aligned that they're only plus minus a degree. How come? That alignment, I, for example, don't understand why this is quite so well aligned, but that's what the evidence seems to indicate. And then it occurred to us that, and this is work in progress actually, unpublished, but very interesting. It occurred to us that one could use it to constrain particle size. Because if these particles are too large, they fall too fast. They fall at, 100 micron ice crystal will have a terminal speed of about 20, 30 centimeters per second, not that slow. And then there's a wake behind it, right? Possibly. How come it doesn't wobble? And if it's less than 10 microns, there is Brownian motion, there's diffraction, there's this and that. And so Brownian motion kicks it around, especially in high cloud. And so where the mean free path is larger. So it's not of academic interest. It really does kick it around. How come only a degree? It's puzzling. So that's what I put here at the bottom. Not too small diffractions, I'll say some in a minute. Too large causes wobble. And there's always turbulence there, even in calm-looking cirrus clouds. So it's so we could put rather stringent constraints on the size of these crystals, right? Because if it's too large, its terminal speed is too high, and I can quantify it. And this is sort of a separate thought. But I wanted to remind you that unlike what we often do here with remote sensing, which is all about optical depths now, this is not so much about optical depths because it's a single bounce. So these photons come after just encounter. So you're sampling more or less the top of the cloud, right? So it's about single bounds, no multiple scattering. And here's the 4 degrees, Vivek, you see? I don't know if that's the same 4 degrees you were mentioning, but I noticed ground observations, everybody looks at, seems to be a rule of thumb, 4 degrees away, right? And your aircraft LiDAR doing the same thing, right? So, but they sample mostly lower clouds, we sample higher clouds, but it's beginning to emerge that this is a very ubiquitous phenomenon. You can't get away from it. You can see it from the bottom, you can see it from the top. It's either that something else is doing it, or these ice crystals are all over the place, right? Mixed there with, because I've seen LiDAR observations of these kinds of specular returns in northern clouds, mixed phase mesoclouds from the bottom. And these ice crystals were, I think, below supercooled water. So they're all over the place, and they're so well aligned. How come? If it's that messy. So here I'm just putting it slightly differently to illustrate how we could use it to constrain the size of. But the notion that one could constrain the tens or 100 microparticle sizes from 1 million miles away is kind of interesting, huh? It's very surprising. But so what are the sources of angular spread? I guess we shouldn't forget diffraction, which is lambda over d roughly. And so I put in some numbers literally last night at half a micron, and just to give a ballpark estimate. So it's on the order of a degree. So you see half a micron, it's just visible light. So 50 micron particle then is giving you that degree. So specular, so this is the width of this lobe, right? So it pushes out to small, the conclusion is it pushes out to small ice crystals, less than, say, 50 microns. I think it's even more stringent than that. But we are ruling out diffraction because there is no color dependence. You see, if this were lambda over, if diffraction dominated this, then the red, lambda red is about 1.5 lambda blue, right? So you would think that red glints would be broader statistically after you're done with a couple of years of observations, but they're not. So we're ruling out diffraction. And then when I go from this optics to kind of summarize it, and on the left is a picture with, you've seen this pattern, for example, with fallen leaves. Now it's much larger objects, but actually fluid mechanics is somewhat similar. And so certainly not a degree, right? Certainly not restricted to a degree. So lambda, so diffraction part is overruled. People often forget that also there is a angular width to the sun, half a degree. So when we draw parallel rays, they're only so parallel, right? Right? Parallel, but to within half a degree. Even if we assume that ray optics dominates. So, and here I decided to, this is maybe a little bit more quantitative slide, but just to put it all together, again, the idea is particles are not too large and not too small, but laboratory experiments for disks, so hexagonal plates have no exact solutions. Fluid mechanics in that regard is not so easy either because the exact solutions exist only for so-called laminar flow, Stokes flow. But if we are in a laminar flow, it pushes out to the Reynolds number. See, Reynolds number, if you need to recall, it's defined at the bottom. It's speed, which in this case terminal speed, times size of the particle, divided by kinematic viscosity. And so the fall speed in the Stokes regime is unlike a sphere, which is quadratic with size. This one is, disk is linear with size. I picked disk because that's the closest thing to a plate that's available in closed form. And, but then the question is, is that the only option? And I don't know. Maybe if you have any ideas, let me know. This is why this girl with a pearl earring portrait came up, because clearly objects can be somewhat slightly curved, don't have to be plates, and still produce a glint. But again, it's a very strict conditions on the curvature of the particle. So, and here I'm coming to the very end of my understanding. Okay, could it be plates? Could it be something else here that's much more easily maintains alignment? And of course, that's pretty difficult. I'm sure you know it better than I do about various forms of ice crystals, at what height. And so it's still open. It's still open. We were kind of going with the upper left, this hexagonal plate. That was our idea of those plates. And another thing is that we see them all over the place. So we don't have very good height measurement. It comes from this A and B absorption bands. It's plus or minus a couple of kilometers sometimes. But it does seem, from all kinds of indirect evidence, that this occurs all over the place. High clouds, low clouds, cirrus, Edmondson, big clouds. See the glints, you know? It's all, if the clouds are there, we always see them. Not super glintsome, but you know, always see them. So what particles producing what shape, and why is it so well aligned to within a degree? That's a kind of a puzzle. And so here, that's basically it for this ice crystal. But I thought I thought be interesting because I know people here deal with ice crystals. And how am I doing on time? Okay. Yeah. And my next topic is actually also, it just appeared. So I included it simply because it's the most recent thing I've done. And it's interesting. I think you might like it. And you could see it with aircraft. And so, and that is the result of the three co-authors here are all from Israel. And my friend Elon he's at the Weizmann Institute of Science, which I visited probably some 15 or 16 times in the past 20 years. And very nice group. And this was almost, again, kind of random walk, almost by accident. So that lambda over D was on my mind. And antenna people and radar people know it better than I do, that lambda over D is an estimate for a main lobe, right, John? So main lobe of the antenna, for example. And so it's nothing new, but I happened to see how to make the whole thing very simple. So let me tell you, this will be easier. But first, let me remind you of Glories. Another thing that helped me, I saw it with my own eyes for the first time about a year and a half ago, flying back home to Upper Michigan. And so let me remind you what the glory is. And so glory requires, it's a backscatter phenomenon, and it's backscatter from raindrops. Or, I'm sorry, cloud droplets. Usually cloud droplets. And so typically people see it from an airplane. I did. And so that's why I started with this picture. So if you're sitting in that airplane, the sun is behind you, right? The sun is behind you, and you're looking down, and this phenomenon requires a strict alignment of sun, the observer, and the cloud, right? Sun, observer, and the cloud. And the shadow of the aircraft is incidental here. Just you happen to be in the aircraft, but so the sun is behind us, and what we observe is just slightly off backscatter, right? This, and it's as typically with atmospheric optics, halos, coronas are about diffraction, but bows like rainbows, now that's usually about refraction. So index of refraction. Here, index of refraction is less important. You'll see in a minute. But so does that make sense so far? So the sun is behind us, we're looking down at the cloud, right? And it's, yeah. And so, and the aircraft is not maybe so important because you see it at the top of the mountain. Here's another example. And that's around people's, could be around observer's head, for example, and so, right? And that's why it had all kinds of, its history is also very interesting, halos and religion. But that's the idea. So we see it. And so when I went to Israel this time, I don't know if you can see it, but this friend of mine, Elon, has amazing eyes. He's just very good at observation. And also he's been doing it for the last 20, 30 years. He just warms up every day by looking at cloud fields. And he told me about this first time maybe 10 years ago, and I just didn't react. And then again, this time it clicked. And so what you see, can you see it? Can you see the faint elliptical colorful shape on the left? Can you see it? If you really, it's faint, that's why I called it faint. Can you tell? It's right around here. Oh, I can use a cursor. You cannot see, huh? I was worried. See, I didn't want to lie to you, and I wanted to kind of come close to what actually happened. On his computer screen, which was a large Mac, we could see it. Oops. But it's, so, can anybody see the slight colors here? It's a little yellowish, green, huh? Yeah, you can see it? So it's hard to spot it, right? But you see them. You see them if you really try hard. And then, so the elliptical shape is mostly due to processing. This is MODIS pictures. And people here know about MODIS, right? Yeah. And so my contribution was to the simple formula in the parentheses. I mean, you could literally, I just happened to see it, and then I wanted to know about the pixel size and the size. It happened to be about, I think, 70 kilometers, the width of this glory. So we're looking together on his screen, and the white border is nearby, and 70 kilometers. I just compute the width, right? I compute the width, and the satellite is about 700 kilometers high, right? So all you do is you say, 70 kilometers divided by 700 kilometers to ballpark it. That's 1/10, 6 degrees, take half of that. And then the second part is you set it equal to wavelengths divided by particle size. So what does it take to do 6 or 7 degrees? 1/10, right? The droplet size should be 10 times, I'm ignoring a factor of 2, just to illustrate the argument, 10 times, it's amazingly simple, 10 times the wavelength. And so you get, as a first estimate, without the factor of 2, we then did the calculation as a 5 micron, and you get 10 microns, turned out to be a little bit larger. The point is, without any kind of effective radius, without any other very complex retrieval algorithms, again, this, like a glint, is also a single bounce phenomenon, right? So you're sampling, Glory is a single bounce phenomenon too. It's backscatter now, but, or near backscatter, but it's, and so here's delta theta, and you, from this delta theta, from the angular spread of the Glory, you just get the particle size, period. Then it's a little harder to argue what kind of size is it. Turns out that bigger particles reflect a little more than little particles, so slightly shifted towards larger size. So it does have some mild dependent size distribution, but it's pretty mild. And so, and that's the whole story. I wanted to, so the whole story is summarized here. So I'm repeating that panel, but I wanted to enlarge. So the Glory is, if you think of miscattering, the Glory in this little part is bunny here, this backscatter, right? And there's a couple of peaks. What surprised us, now I had no business of guessing lambda over d because we have a mesoary exact solution for spherical particles. How come there's no index of refraction in this formula? And, you know, it's sort of separation of church and state here. Somehow it works out that despite the tremendous sensitivity of the solution to intensity to this change, you take a tiny little change in particle or in size parameter, and an intensity diagram totally changes. but somehow the angular scaling survived. So I don't fully understand why, but it's almost opposite of a rainbow. Rainbow, the physics is all about refraction, and here the physics is about diffraction, right? And then, and so this is to make that point that the panel D is, despite all that sensitivity, there is some kind of factorization going on. The diffraction scaling survives in spite, and it survives some variation in the index of refraction too. So you have me theory, right? We all know that it's an exact solution for a sphere. And Glory, by the way, is very, very sensitive to spherical shape. Disturb it slightly, and it disappears. And so, so the human eye picks it out very nicely. It's faint, but it's a color phenomena. But we now know we can detect them also in the invisible. Nakajima had a paper already in the 90s. I just learned of it recently, that detected it in near infrared, 3.6 microns. But then it's a single color kind of thing, so you don't see it as colored rings. So this part C here, the diffraction scaling survives, is still a bit of a mystery. But to me, at least, because when you look at the exact solution, they're always entwined in every step of the way, the refraction and the diffraction. So why did it separate? And so we did it. It was a proof of concept kind of paper, very short. Proof of concept, and did it on marine stratocumuli. And so this is that same faint glory here on panel B. Same one that I showed you, very faint here, right? But here it's a difference of two channels, red and blue. And then this little rectangle is where we pick, oops, sorry, I lose my cursor. Here, that's right. The rectangle, this is where the transect, this is from where transected C is taken. And so you can eyeball it, and literally, and it was one paragraph in the paper, you can estimate the size. But then you can also automate it because the satellite carries the information. It's also very simple. You just give me the distance between the two peaks, and then we'll get the size from there.
Alex, from the plane it was circular, and this is very oval. What's the reason why this is distorted?
Yeah. Yeah, thank you. Thank you very much. It's a good, yeah. Oh, you want to repeat it? Oh. Yeah, so it's a great point. So why is this glory of elliptical shape? So one reason is satellite processing. So I don't know how to, it's this push broom mechanism, so it kind of elongates it. But another reason is that as you go, even within this transect, the width changes because the drop size changes, I think. It's my understanding. Lambda over D, right? But the drop, lambda is the same, D increases, then the glory narrows, right? But overall, ovalloidal shape, it's due to the modus processing, I think. This push broom goes in and out. And that's why. And it's, so we're going to work on the automating it because actually in this paper, the pictures are shown, but the actual processing was done on a single red channel, just the simplest possible, red channel. Just let's fit it to get the distance between the two peaks. Oops, sorry. And that's the end of it actually, but so it seems to me that it opens a possibility for separating horizontal and vertical contribution. That's why I like your point very much, to drop size distribution. You know, we are looking at tops of the clouds, roughly speaking, right? Tops of the clouds. But as you traverse this oval, this ellipsoidal or elliptical-like shape, you can see the variations too. So clearly, as you go through this cloud field, drop size changes as well. And so there is some variation vertically, but then we are within one mean free path. And in many ways, it's complementary to existing techniques. We are looking at the top of a cloud. This works best when clouds are thin.
So does that require that you have liquid water at the top?
Yeah, they're all marine stratocumuli, off the coast of Kirk. They're all warm, I think. But I don't see any reason why it shouldn't work for supercooled water either, as long as it's spherical. Even if it's messy, I think it should show. By messy, I mean mixed supercooled water, but with some occasional ice. What it really wants is a spherical shape. And so we think it's very promising, and they're all over the place. Basically, if you know where to look, in this little paper we give kind of a succession of points. Solar nadir, the satellite nadir, the glint is in between, and then there is a glory. Then you can see it. But the problem is that data is often very noisy. By noise I really don't mean any instrumental noise, but inhomogeneities, fluctuations in cloud properties themselves. And they can occur at high frequency. Here, pixel size is about 500 meters, I think. But clouds vary even on that scale. So usually they wash out. It's one of the prettiest glories that we found in terms of the transect. But it gets buried in second. How would I put it? My rule of thumb at the moment is that if you don't see, this our preliminary calculations show that if you can see the second peak, it probably means it's very narrow distribution, plus minus a couple of microns. That's another interesting thing that they could be. What you want is small, relatively thin clouds, and monodispersed or narrow distributions work best. Otherwise, they're shifted, but glory can be washed out with a broad distribution. So, so that's about it. What an interesting adventure with glories, but I think they could be seen with all kinds of instruments. So, and how am I doing? I'm a little bit late. So, but that's okay. I wanted to just give you a flavor for what we do with signals in case there are lots of data here at UL that maybe some of it we can benefit from this technique. So maybe I'll just I still have 5 minutes, right? So I'm thinking here about time series. And so I'm switching gears totally to mathematics. But it's mathematics of relevance to us. It's mathematics of signals and noise. So we got into this field of ranking data, and it began with record-breaking statistics. But we ended up with rank. So at first it shows little promise because rank doesn't know about magnitude information. And because it doesn't know about magnitude information, you'd think, well, it just loses all the functional information about functional form, as illustrated here. But it turns out in the opposite regime, which is of usually most interest to us, and that is weak signals, signals that really are very hard to determine by any other means, very, very weak, feeble, then it picks it up. So I'll just illustrate it on this notion. So suppose you're watching the same thing with several instruments, and you have a bunch of time series, same phenomenon, and it helped us to define noise. So the way we define noise, electrical engineers will understand me that so-called IID noise, it's written here, right? Independent and identically distributed. It means what? It means that at every point in the time series, at every time slot, I'm drawing from a distribution which is identical from slot to slot, but also statistically independent. Only that kind of noise has the symmetry that I might take so I rank the data, I take the time series, and if I switch the coordinates on you, I switch rank and time, you would not notice by statistical properties. It's the only kind of noise which is uniform and has this total symmetry, this duality between the rank and time. And by time, of course, I mean order parameter. It could be space, could be something else, order, time sequence. And then we decided to lift this one-dimensional time into a rank time plane. And so this capital U here stands for uniform distribution. So only pure noise, pure in the sense of this IID, can tell the difference. I'm sorry, cannot tell the difference between rank and time. And now so it led to some other things. Let me point out that maybe I'm still learning how to explain it simply, and we are clarifying this. But this is a technique that can work with any of your favorite method of signal extraction. How? Extract your signal any way, which way you want. Give me your residual. I'll look at the residual and I'll check how close it is statistically, without any assumptions, any parameters, to pure noise, IID noise. And if it's within 3 or 4 standard deviations, great, you probably did a great job. And if it is 10 standard deviations, maybe without any parameters, non-parameter, then maybe there's more signal to extract. And signal we understand very broadly, not time-varying mean, but could be a pattern in variance. Maybe your variance is increasing, or high moments. And so, because I took a little long, so there are a couple of slides in construction, but I think I'll skip it and connection with random walks. Here, for example, this is my last couple of slides. Here, I'll just summarize. There was a time series, in this case it happens to be astronomical, but doesn't matter to us. And we raised the question, well, astronomers fitted this data. What's better, one parameter fit or two parameter fit? Two rates to fit or one rate? And we show with this very simple method that there's no reason to, they overfitted the astronomers, basically. There's no reason to, see, this can happen too. Your residual is too good, too uniform. Sometimes they detect fake randomness this way. And so that was one example. And another, I'll finish with that. Another example was that, very interesting, that not all white noise is born equal. And people use white noise. What's white noise? It's not the purest noise in a way, because independent and identically distributed is a narrower set than just white noise, whose spectrum is flat, right? And so here we pointed out an example. Let's just look at panels A and B. B by construction is white in the sense that no correlation between consecutive samples, and but it's not. You see, by construction, this formula, it's formulas that statisticians often use. By construction, it's uncorrelated but dependent and white. And when we look at the variance of this kind of noise, the ends know. End effects seem to always know. We're still working on trying to understand it. It's semi-empirical observation, but experimental mathematics. But somehow the fact that the end of the time series only has one neighbor, not two, picks up that effect of lack of independence. Because correlation coefficient, Pearson correlation, all the stuff we typically use, this is all about linear correlation, right? There could be more subtle correlation. And this method picks it out. And so we learned a few things about signals just by ranking the data. But the latest is even simpler. We ended up with so-called discrete cosine transform. We don't need to rank the data, but that's just... So that's what I've been preoccupied with, just to give you the flavor for the last few years. And thanks so much for coming.
Thanks, Professor Kostinski. We have time for one or two quick questions. Anything online? No.
I can ask a silly question. Yeah, back
I
to
like
the ice
those.
crystals, which I understood more of that maybe than I did some of the
Okay.
other stuff.
I'm going-
And there's this phenomena of this 4 degrees.
Yeah,
So as I understood it, so here's your plate.
yeah.
Right here, my telephone.
Mm-hmm.
And so so here's this plate. Can they see my telephone? And this is, and so you have all these scatters that are in the atmosphere. Are you saying that they have a mean canting angle in one direction or the other that you're picking up? Or I'm trying to understand where that 4 degrees is. I mean, because there's no reason for all these plates to be canted at a particular degree unless there's an electric field or something like that to align the darn things. And so I don't quite understand where that 4 degrees is coming from.
So the 4 degrees, John, is that, yeah, thanks, a great point. And so the mean canting angle, in your terminology, the mean canting angle would be 0. Yeah.
Okay.
But there is a root mean square kind of spread, right?
Right, yeah.
So some crystals are slightly off. The stability here is hydrodynamic. So if they tilt, or can't a bit, right? Tilt a little bit, then there is maybe a fluid flow on the other side, develop some mild vorticity to stabilize it. That's one possibility. And but looking at the plot, this is our optical observational evidence. You see 1/E point, for example, is somewhere under 1 degree on one side. So this tilt of the crystal doesn't exceed a degree or so on either side. So the mean canting angle is 0, but optical evidence suggests that it doesn't exceed a degree. Maybe occasionally two. You know, there could be randomly oriented. It's another model in this field is randomly oriented crystals. And if the crystals were randomly oriented, we would see very broad glints, right? Because there would be enough crystals to reflect at 17 degrees. You know, like for ocean glints, you saw the broader glints because they're tilted facets on the capillary waves, for example, that scatter in the right direction. Here, they're all very narrow. So narrowly focused glints implies to us very small deviation, angular deviation about the mean canting angle of 0. So why? Why are they so well aligned? That's what the question boils down to. Does that make sense?
Yeah. And so, and then you also, from what I understood, you say they don't reflect the phenomena of going through the front surface and then getting bent because of the refractive index and hitting the back surface and then being reflected off the back surface. And that, like it is for a rainbow, I believe that's what causes the refraction for rainbows. And so there's none of this phenomena is taking place in the reflection off your crystals.
No, I think you're right. I think in this case, this specular reflection, I call it reflection, but some refraction could be involved. So this plate is, let's say it's on the order of 100 microns, right? Width, but thickness, I don't know, to be honest. I don't know what to assume, but maybe a micron. So it's comparable to a wavelength, say twice the wavelength. So to discuss that refraction in terms of ray optics is difficult. But maybe that's what should be done. You know, but here I'm thinking about orders of magnitude. So maybe it'll refine it somewhat. But we are more or less assuming that most of the light is reflected back. But some of it probably is refracted. But whatever is refracted, we don't detect. Right?
I don't know. That's what I'm asking you.
Yeah, whatever is it, thanks.
Great question. To be respectful of everyone's time, we'll wrap up here. Professor Kostinski is in town for another week, so it'd be great to continue some of these conversations offline. Let's thank him one more time.
Thank you very much. Thank you.